Okay. So thank you all for having me and for inviting me to talk about this explainable AI. And I'll be talking about it in the context of identifying subseasonal forecasts of opportunity. So to start off, really focusing on why we're looking at the subseasonal bridge between weather and climate with this notably low forecast skill. But the reason that we want to actually focus on this time scale, as I know you're all very well aware, is the benefits for environmental prediction enterprise, saving lives, protecting property and environment, increasing economic vitality, informing policy choices, all things that, these grand scale challenges that are quite important to everyday life. But when we look at this low forecast skill, we don't necessarily, we know that we can't be making really good subseasonal forecasts all of the time. And so instead, we rely on predictable states of the climate system to improve these subseasonal forecasts. And this is where the focus on forecasts of opportunity really comes. So, what we know already is that we have, for example, combined influence of climate modes can lead to forecasts of opportunity. So, one example of this is looking at MJO and ENSO interference. And so, here's an example. MJO contributes a dry anomaly to the southeast US. La Nina also contributes a dry anomaly. We have constructive interference. This amplifies the signal for a dry anomaly in the southeast US. These are just two very specific examples for this is winter time, a specific season. And so then when we look at all of the different contributing factors here and just on S2S timescales, I don't know about everybody else, but this is kind of the face that I make trying to decompose all of these different contributions to an S2S prediction. And so this is the motivator for looking at subseasonal forecasts of opportunity. And so to actually parse this apart, we want to take a data-driven approach. And so we'll be using explainable machine learning techniques to identify forecasts of opportunity and then also explore their sources of predictability. And for today's talk, I'll be talking about two specific examples. The first being wintertime, West Coast precipitation, and the second being summertime, Midwest precipitation with a focus on the source of predictability. So first, explainable machine learning. This is synonymous with explainable artificial intelligence, and you'll hear me use both. The overarching idea here of a neural network is you have some sort of data or input that you then feed through this nonlinear artificial neural network, often seen as a black box, and it outputs some sort of prediction. A little bit more into this, you have your input fed through these hidden layers and it makes an output. It then compares it with the truth, and then based on some user-defined loss function, that information is fed back through the neural network. The weights and biases in these hidden layers are updated. This is what's known as training a neural network to then ultimately optimize this loss function for our predictions. But we want to actually leverage machine learning to actually learn information about the climate system. So as an example, let's say that we give, I kind of give it away, we give the neural network this image here and tell it to predict the number. And let's say it has three choices, a 5, 6, or 7. Using the output from the neural network, we can essentially say there's a 31% chance that this image is a 5, a 2% chance that the image is a 6, and a 67% chance that the image is a 7. The network then predicts that it's a 7, and in this way, we actually quantify the confidence in the probability of the predicted output. And then next, we actually want to understand, what did the network learn? As climate scientists, it's really important not to just make good predictions, but to understand why. And so this is where these methods of explainable artificial intelligence, or XAI, actually aim to explain how a neural network makes its predictions. We're looking at the decision-making strategy via what we call attribution or explanation relevance heat maps. And so why XAI is so important here is because we can build trust in these black box models. We can fine tune and optimize. We can do things better, but we can do them quicker. We can do them cheaper. And ultimately, we can learn new science. And really what I'm focused on here are these two primarily as the benefits of XAI. So here's an example. Let's say now, instead of the 7, we have an image of this bird, and we feed it through the neural network, and it predicts that it's a junco bird. But what we want to do is figure out why it predicted that it was a junco bird. So we go back into the neural network, open the black box, if you will, and we can actually make heat maps of the individual pixels that were important to making the prediction. So we see here the beak was really important, the eyeball, the outline of the bird. And now we can understand why the network predicted what it predicted. And also using our knowledge as climate scientists, we can look at perhaps spurious sources here and using both the neural network setup and our knowledge base as climate scientists to explore sources of predictability. So first, we'll be looking at tropical convection as a subseasonal predictor of wintertime West Coast precipitation. And I had a number of colleagues working with me on this. And first, we'll start with our neural network setup. We take maps of tropical precipitation anomalies, as you can see here, where each grid point is an individual predictor. We then feed this through our neural network, and we are predicting the sign of the anomaly in these 3 boxes along the US West Coast: Alaska, Pacific Northwest, and California. And we're making this prediction on a week 4 to 5 timescale. So we have tropical daily tropical precipitation anomaly maps to make a week 4 to 5 prediction, whether it's above or below normal in these 3 boxes. So we're asking, can tropical precipitation be a subseasonal predictor of US West Coast rainfall? And so the data that we're using here, machine learning is very data hungry. And so we utilize the CESM2 large ensemble. We take 10 members from that ensemble. We use 1850 to 1950, November to March, and we compute the daily anomalies by removing the ensemble mean. The first thing that we want to do is assess the network performance. So here we have these boxes here showing the accuracy of those week 4 to 5 predictions for 100 years in each of our 3 regions. The gray X's here are showing what the model would predict by random chance. And so each of these is a different ensemble member that has been trained individually. And so what we see here is that for each of the 3 regions, our accuracy exceeds that of random chance. But as we discussed, just making predictions above random chance isn't really good enough. And so we want to quantify the confidence of the neural network's predictions. And so we can rank the predictions by confidence. And so that's exactly what we have here. So this is showing all of the predictions, but then with that confidence that's associated with each prediction, we can then rank the predictions in terms of confidence, where we have the 50%, 40%, up to the 10% most confident. And on the y-axis here, we have the accuracy of each of those predictions. And what we see is that as confidence increases in a prediction, accuracy also increases. And so by definition, these predictions are made from more predictable time periods. And so if we isolate the 20% most confident predictions, these are also the most accurate predictions, which are by definition forecasts of opportunity. And so we now go back and we can compute the accuracy just of those forecasts of opportunity. That's what we have here in the diamonds. And what we can see for each of the three predicted regions, the accuracy of our forecasts of opportunity exceed that of your average accuracy. And so we have now used this machine learning approach to identify predictions that then result in a forecast of opportunity. Next, we want to understand, what did the neural network learn? And so we use these XAI, this explainable AI techniques, to now make these relevance heat maps of the actual input maps. And so here, this is for California, for a negative anomaly and a positive anomaly on that week 4 to 5 time scale. And the purple colors are indicating more relevant features. And so, especially for a positive sign anomaly, we see that the central tropical Pacific is really important. This aligns well with our knowledge of ENSO teleconnections to California rainfall. But we also see that the Indian Ocean, often associated with the MJO, is also really relevant to making a forecast of opportunity. If we then expand this to our other predicted regions, we now see again this tropical Pacific region, but for Alaska and the Pacific Northwest, it's actually shifted westward. This pattern that we see here of relevance is actually really representative of the CESM and so related rainfall. And then we also see regions around the maritime continent, often associated with the MJO, that also lead to predictability. And so we find that this XAI is actually revealing physically meaningful sources of predictability that are associated with periods of enhanced skill. This is gaining trust and ultimately learning new science via this explainable machine learning setup. And then a very reasonable question to ask would be, well, all of this happened in CESM, but what about the real world? And so we then take these neural networks trained from 1850 to 1950 on CESM2 data, and we then test ERA 5 data from 1959 to 2021. And here, where our boxes are the accuracy from all predictions, the diamonds are the accuracy from the forecast of opportunity, the 20% most confident, and the X's are random chance. And particularly for the forecast of opportunity, we are exceeding random chance. And so the networks have identified predictable states of the climate system within CESM that are actually useful for making accurate subseasonal precipitation predictions in the real world. And so now we are able to take these machine learning models trained on climate model data and actually learn information about the real world while also quantifying and identifying forecasts of opportunity. So now changing gears a little bit to summertime precipitation in the Midwest, but instead of using tropical convection, we're now exploring using sea surface salinity as a subseasonal predictor of summertime Midwest precipitation. And again, I have a number of collaborators working on this with me. So first is, how can sea surface salinity actually help predict landfalling precipitation? And so here we have this image, this cartoon of your classic water cycle, where essentially it's this closed water circuit of recycling and raining. But in reality, the evaporation that happens over the oceans, let's say about 86% of that evaporation, only about 78% actually rains back out over water. And so what this means is that about 10% of the water that evaporates over the ocean actually gets transported and ultimately rains out over land. And so we want to explore, is there predictability in that 10% remaining that can actually help us predict landfall, land rainfall and extremes. So first, there's been a number of studies that have shown that the moisture supply, especially for extreme rainfall over land, that moisture has an oceanic origin. And then intense and persistent precipitation events over land can't be sustained by local moisture recycling alone. Lastly, we specifically use sea surface salinity as an indicator of that evaporation and ultimately moisture export from the ocean. And so a previous study by Lee et al. In 2018 showed this on a seasonal timescale, where they showed that evaporation in the Gulf of Mexico and North Atlantic region ultimately led to moisture being transported and additional water availability in the southern US, which then ultimately re-evaporates and is transported to the Midwest, ultimately raining out. And so we wanted to see, can sea surface salinity be instead a subseasonal predictor of US Midwest rainfall? And so we take a very similar approach here with an artificial neural network setup. And again, we're using CESM, large ensemble, 10 ensemble members from 1850 to 1950. But now we're using 3-day average sea surface salinity anomalies in the North Atlantic and Caribbean Gulf of Mexico region from May to August. And what we are predicting is rainfall in this Midwest boxed region. But it's now a 3-day cumulative sum of rainfall, and we're determining whether it is a light rainfall event or a heavy rainfall event. Heavy rainfall event is determined by being 80th or above percentile of rain. But we are randomly undersampling our data to balance our classes for this neural network approach. And so 50% here is going to be random chance, similar to the previous problem. Now, a note on how we are actually dividing up these classes is via this Poisson weighting. And so we take a Poisson weighting approach to have a more seamless transition from the 1 day to 1 week to 2 week to 3 month time scales here, where we know that the farther out in time that we make predictions, skill drops. And so we wanted to have a more fair comparison across time scales. And so we apply a simple Poisson distribution to our output, that 3-day cumulative sum rainfall in the Midwest. The reason that we're doing this is because it's broadening the event window as lead time increases, moving us from a deterministic forecast to a probabilistic forecast. It expands to a range of maximal forecast lead times. And so we're able to go out from here out to 8 weeks, improving transferability between models. And then it's also really cheap. It's very straightforward to actually implement in the data. And so what we're actually doing here is this blue and black line here is the raw time series of the 3-day cumulative sum for 1 year. And then based on the lead time from 0 to 8 weeks, we apply this Poisson weighting, and it's essentially smoothing the data based on lead time. We then compute the 80th percentile, and any event that exceeds the 80th percentile is considered a heavy rainfall event. So we now take a very similar approach here, where first we want to assess the network performance. And now we have leads from 0 to 8 weeks, where our squares here are showing the accuracy for all predictions. And each of these boxes here is again another test ensemble member. We see that accuracy actually increases as we move out in lead time, peaking around weeks 2 to 4 lead time, but then decreasing where we almost lose all skill when we get to leads 6, 7, and 8. We then quantify the confidence of the neural network's predictions to ultimately identify our forecasts of opportunity. And I should note here too that these gray lines are showing random models, an untrained model. So it is not guaranteed that accuracy does increase as a function of confidence. However, for these predictions, because there is predictability, there are signals to be learned within these input maps, these sea surface salinity maps that we're giving the neural network. We again see that the accuracy increases as a function of confidence. I'm showing specifically here the 3-week lead, but we see similar for 2 out to about 5 weeks, and then these accuracies drop to about random chance at beyond 6 weeks. Again, we isolate our 20% most confident, which are also our most accurate predictions. And so we have now identified more predictable time periods. And so we then look at the accuracy of our forecast of opportunity also as a function of lead time. Our accuracy for these forecasts of opportunity far exceeds the accuracy of all predictions, but we do see this predictability really drop off at lead 6 and beyond. And we also see that the accuracy of lead weeks 1 out to lead 4 actually remains about the same and pretty high. We're at about a 75% accuracy specifically for these most confident forecasts on these subseasonal leads. Next, of course, we then want to figure out what did the network learn about these sea surface salinity maps. So first, again, I'm showing the 3-week lead because that's where we had the highest accuracy, but it doesn't vary too much between weeks 2 to 5. Purple here, again, being more relevant to making a forecast of opportunity, making a confident and correct prediction. We see here that the Caribbean Sea is very important to making these predictions, as well as the North Atlantic, especially Gulf region. Now, I will make one note that these are for the light predictions and these are heavy, but because this is a binary classification problem, the neural network is going to learn individual grid points and what's important. So the fact that the Caribbean Sea is really important for light predictions also implies that it's important for making heavy precipitation forecasts. Now, the next thing is that sea surface salinity is not a widely used input or predictor. And so we also want to understand what actually is happening in these input maps that is leading to this enhanced forecast skill. So we then composite the maps that ultimately led to a forecast of opportunity. On the top here, we have maps that then led to a light precipitation prediction 3 weeks later. And on the bottom, we have the maps composited that led to a heavy precipitation event 3 weeks later, or prediction. Green here is a positive sea surface salinity anomaly indicating saltier waters, and it's an indicator of evaporation. Vice versa, the pink colors indicate fresher water, negative sea surface salinity anomalies, or precipitation. So we see here for these heavy precipitation events, we have these really prominent salty anomalies in the Caribbean Sea, indicating evaporation in this area. And so we also know that this is the location of the Caribbean low-level jet, which then ultimately coincides with the Great Plains low-level jet to ultimately transport water to the Midwest. And we're seeing this here just in these composite maps with a 3-week lead. So what this is showing is that these positive sea surface salinity anomalies can actually provide predictability for summertime Midwest heavy rainfall events on subseasonal timescales. The next question then is, what about the real world? And so instead of taking daily reanalysis data of sea surface salinity, which is not super available or even highly trusted, we actually used a water accounting model known as the WAM2 to calculate moisture recycling ratios. So it's essentially a water tracking model, and it tracks where evaporation occurred that ultimately rained out as precipitation in a specific region. The data that we're using here is ERA interim hourly data 2008 to 2021. And so what we have here is this box over the Midwest. This is the same box as we were making predictions in. We take this box and we say that for any rainfall that fell between May and August in the 2008 to 2021, where did that water originate? And so the darker blue colors here are showing where that water originated from. Darker blue just meaning more water originated from that area. Not surprisingly, that water originated in that area. So it then evaporated and rained out there. But we do see that a good amount of water actually came from the southern part of the US, as well as water sources in the Gulf of Mexico and the Caribbean Sea. So we then ran another round through this water tracking model. Note that this is an order of magnitude smaller, but we wanted to also find out where this water came from that ultimately rained out in the Midwest. And again, we really see this clear signal of this Gulf of Mexico and Caribbean Sea origin. And so the regions of evaporation that were actually identified by our neural networks that provided subseasonal predictability actually have shown to have oceanic origin to rain out in the Midwest. And so to come back to our overarching goal here, we want to identify subseasonal forecasts of opportunity, and we take a data-driven approach to not only identify these forecasts of opportunity, quantifying the confidence associated with these predictions, but also to highlight and explore sources of predictability on this subseasonal timescale. We quantified the predictability provided from the tropics for wintertime West Coast precipitation anomalies. And we have also been exploring sea surface salinity as a predictor for summertime Midwest heavy precipitation events. We found that for both of these studies, the relationships and the sources of predictability that we identified with the neural networks were actually present in modern reanalysis data. And ultimately, this leads to increased skill and confidence in our regionalized subseasonal forecasts. So I will wrap it up there and take questions.
Thank you. This was, I think, second time I was hearing this presentation, so I'll not ask the same question. I'll ask a different question. So for at least the CSM part, have you compared your result with the corresponding subseasonal forecast, sub-X forecast? And is the skill here that you are getting out of the machine learning or neural network model, is it greater than what is subseasonal forecast is showing? Or like what improvement we are getting in terms of the this neural network compared to the traditional climate model based forecast?
Yeah, so to answer your first question, we have not actually compared skill with sub-X models. And the reason is because they're very different setups. So sub-X is using as much information as possible to make the best prediction possible. And we, for these two problems, we were using just tropical precipitation to make week 4 to 5 predictions. And in the second one, we were using just those Gulf of Mexico and North Atlantic sea surface salinity maps to make subseasonal predictions. And so it would not really be an apples to apples comparison in terms of skill, just because the entire setup would be different. How I see this blending into a question like that would be we're using these XAI techniques to help identify new and additional sources of predictability, to also understand why we are making forecasts of opportunity. And that can be really transferred to a sub-X type framework.
Yeah. Thank you. Very nice presentation. So I think it's pretty impressive to see this week 4 to 5 prediction skill in the US West and Alaska. So my question is that you have shown these skills mainly from the MGO and also the ENSO. If I remember correctly, the MGO prediction skill is about 24, 25 days in CESM. And also the ENSO related precipitation also have this kind of westward shifted bias in most of the models. So I'm curious how this week 4-5 skill comes from because of this limited prediction of MGO and also the ENSO related precipitation.
Yeah, that's a great question. So, we, instead of, um, using the MJO and ENSO specifically as inputs, we just took a really agnostic approach here of just giving the daily tropical precipitation maps. And so when we use the XAI heat maps to show relevance, we saw these ENSO associated regions, these MJO associated regions. But this is not specifically given MJO and ENSO information. And so what that means is that there is longer term predictability that is able to be extracted from those daily preset maps that are also evolving in time. So it's not specifically highlighting the predictability associated with CESM MJO.
Yeah, I just got a clarification. So when you're showing the salinity heat maps for the high and light precipitation, yeah, the left-hand panels, you mentioned something that the map on the top could also be relevant for the heavy precip, and I didn't quite catch that. If you could just walk me through.
Yeah, so if you notice here, the most relevant regions are really shown in the light precipitation map. But what we found here is that the evaporation in the Caribbean Sea, Gulf of Mexico region, that evaporation then leads to more moisture availability that then is transported over the United States, ultimately raining out in the Midwest. And so I just want to make clear that it's not just that this region is important for making a light precipitation prediction. It's important for making both. And just because the neural networks were only given two options as an output, a light or a heavy, the fact that the neural network has learned that these grid boxes here are important for determining whether it's a light prediction, it is also then important for making a heavy prediction. It is looking in this area to actually see what the sea surface salinity map is doing to ultimately make its prediction. So the salinity anomalies, whether it's salty or fresh in the Caribbean Sea, is important for making that subseasonal prediction.
Gotcha. I guess I'm confused at why then it doesn't show up on the heavy precip map
Yeah,
below. It's because it
again,
can only
that's
be on one because it's a yes or no question.
exactly. And so it just what is like built into, this anomaly, the neural network has determined that it's easier to learn these fresh anomalies for making its prediction. But we often see, especially for looking at like the 20% most confident for a binary classification problem, that usually the really relevant regions in one don't appear in the other because it's just learned that that grid cell is important to look at.
Okay, cool. Thanks. Yeah, appreciate that.
I'm curious about, I guess I'm curious about the accuracy statistic used, but I'm also interested in other benchmark forecasts. So did you look at persistence, for example, other than a random forecast? And I'd be curious to see sort of, yes, you're making a week 3 or week 4 forecast, but what about rolling over the week 1 or the week 2? And what kind of skill do you get just from that benchmark? That's my number 1. And then number 2, summertime convection in the Midwest is like 90% driven by mesoscale convective systems. our predictability of those on a daily time scale and even a weekly time scale is not good, maybe 3 or 4 days. So I'm wondering if the salinity aspect is capturing other things in weather regimes or other large-scale atmospheric patterns that are driving back to hold an atmospheric regime in a predictable pattern, sort of whether you call it blocking or whatever, versus this predictability that you're getting from salinity.
Yeah, so first question is one thing that we are working on now for the benchmark question is computing some recall and precision type computation. So basically looking at false alarms, mishits, that type of thing, especially because for looking at these extreme events, if you will, this 80th percentile, they occur a quarter of the time. So by looking at those sorts of benchmarks for the contingency tables is another metric that we also want to use to help convey these sorts of results and also looking at those predictive signals. Then for the timescale aspect of this, so when we look at the accuracy, the lead 0, so making the 3-day forecast for starting tomorrow is actually lower, and then it increases as we go out to lead week 2 and 3. And the reason that I hypothesize this is because of exactly what you were talking about, where the sea surface salinity maps are indicative of evaporation. And so that evaporation then occurs and then ultimately needs to be transported, especially from all the way from the Caribbean Sea via these low-level jets up to the Midwest region. And so this is why we see that we have the highest skill on the 2 to 3 week lead time, while the 0 to 1 is really going to be driven by those mesoscale systems like you mentioned.
And I think the other thing too, I'll just quickly interject. I think the other thing too is I wonder if sea surface salinity really, I don't know if this is exactly what Victor was also getting at, but the sea surface salinity may also be a signal of actually the atmospheric pattern itself over the Caribbean. So for example, if there is sort of persistent high pressure there that's forcing higher evaporation, that could then have upstream or downstream effects that would then affect the precipitation patterns across the US or downstream across the Atlantic or something. So in other words, sea surface salinity is sort of a tracer of something going on, so to speak, but it may not be the actual driving, or could be not the actual driving, it's just a representative thing. Anyways, okay,
Definitely.
I have,
so on that point, so when we look at the water accounting model, we see that the moisture originated in this region that ultimately rains out. But I actually tested sea surface salinity anomalies that extended all the way down to the South Atlantic. And we found that the tropical Atlantic sea surface salinity anomalies were really indicative of Midwest precip. But ultimately, when I looked more into it, I found that the sea surface salinity maps were really just capturing the Atlantic ITCZ, which is then going to ultimately impact the circulation patterns and everything like you're saying. So instead, by focusing just on the regions that we know for sure evaporation, that moisture has originated from, we can then take these maps and put a predictability component on it.
I'll kind of echo a couple of comments. That was a very nice presentation. I like to see these machine learning presentations where there's at least some thought given to how to explain them, because I think when you think in the context of some of the things we're interested in, where it's not just a matter of making the prediction, but communicating this in an application sense, it's going to be always important to do that. And so this kind of explainable AI, and even beyond that, just explaining how the technique works is important. Also with Victor, I have the same feeling about the metric, but you've answered that, so I'm good on that. And yeah, along these same lines, I would say that, the biggest moisture gradient in the atmosphere is in the vertical, not in the horizontal. And all you really, not all, but often all you need is just strong upward motion for downward motion, and there's your precip anomaly, and that's the thing that you have to predict. But what I'm actually interested in here is the question of how you deal with the trend, because you're using the large ensemble, right? So these have a historical forcing, and it's not clear to me how much you're able to separate out either the effect of the trend, and if it's not separated out, a lot of the skill could be coming from basically predicting the trend, or alternatively, whether there's a change in the relationship that you're not able to capture because you're using all of the data just kind of mixed together. Do you have any sense of that? Have you thought about that at all?
Yeah, definitely. So something I should have mentioned is that for both of these projects, we did detrend the data, the CESM data, by calculating a linear trend in over the ensemble mean of the 10 ensemble members. But it was quite small because it was 1850 to 1950. So that was really the motivating factor for using that time period. But then in recent history, we still we have a larger trend, as you mentioned. And so we were, if you notice that skill in the Aero 5 data for the West Coast did decrease. And one element of that is that it's a different model and a different time period. But I also do think that part of that skill is lost because now we are in a different climate system, like you said. I also think that when looking out into the future, if we were to make future projections and explore this type of predictability, these sources of predictability in future climates, that becomes even more important of the role of the trend in, influencing the predictability.
Yeah, this is just more from a forecaster standpoint, and you may have not thought about this and looked at this, but I'm just curious if because my interest is the cross validation, and I can see that you guys are making an effort to keep your training data set separate from the verification data set, which is great.
Yeah.
There's this little concept called predictor screening that Tim Del Sol and Mike Tippett published on many years ago. And the idea is that you can inadvertently select essentially predictors from your data that you have that are known because you're working with the historical data. So they did this fun little thing, and maybe you could do it on the side if you haven't had these discussions already. They basically put in random numbers as their input to their model. All right. So in your example, you used daily tropical precipitation. And so I'm curious if you just inputted random numbers, white noise, into your model, would it find predictors?
Mm-hmm.
I mean, I don't know if anyone in your group or you have ever tried that, but it could help at least settle that question, whether there's some advantage here.
Yeah. So I haven't done the random numbers, but I have input maps of just zeros because these are anomalies. So like there's essentially no information. And then skill is just completely lost. Now, on any given prediction, you can be right, but it's like looking over the whole time period. But that's a great idea. I will
Yeah,
try the
I'm just
random.
curious, nerdy curious, and I'll send you that paper because it is something that comes up every now and then. Thanks so
Yeah.
much for the talk. It was really
Thank you.
excellent. You described everything really well.
Thank you.
All right. Well, thank you again, Marybeth. We really appreciated the talk. It was very informative. Excellent job. And I guess now we'll kind of move on to our panel business. So thanks again, Marybeth.
Yeah, thank you for having me.